Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salam ala Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamu alaikum everyone. We're going to be continuing with the stabilization control on SO3. So let's start with a recap. As usual, today we're going to be looking at designing a controller for rigid body dynamics on SO3, so for a rotating rigid body. And the controller will have two terms, a proportional term and a derivative term, so essentially it's just a PD controller. However, in order to design it, we're going to be interpreting it as that the potential term actually is doing something like energy shaping, and the damping term is damping injection to the system. Okay, so with regard to the energy shaping term, so the proportional term, we choose it from as the gradient of some potential function psi. So this psi we design it such that it will have the desired position, okay, or desired configuration to be a minimum of it. And afterwards, then we actually will show that usually we get V dot is equal to something that looks like this, right? So where V is the conjugate variable of this, so it's related to the psi dot, and the UD is the input that we want to design. So we're left now with another control input, the derivative term or the damping term, and then we just choose it such that it's some sort of negative function of the V, it's negative definite function, such that in the end we have that V dot is, we would ideally think about, let's have this negative semi-negative definite, but usually we just end up with negative semi-definiteness, and then we go to Lassalle's theorem and so on, and we move to show actually that we do have the point, the state that we want to go to, which is the desired configuration and the zero velocity, because it's a stabilization problem, to be locally asymptotically stable, and then provided that actually the space itself allows you to find a globally asymptotically, that the desired point is a global minimum, then we have global asymptotic stability. Okay, but usually that's not the case. Okay, and it's not just about the function itself that's not permitting it. So usually the problem itself doesn't allow you to have this form. In this case, so this is how we reinterpreted the PD controller on R3. And then we said now in exactly the same way we can design the controller on SO3 and in general on different manifolds. And that's why we took the SO3 problem. So we took the rotation of a rigid body, and we said that the state is the configuration and P is the angular momentum. We have, this is the equations of motion as we've seen before. And the beta here, so because the beta will pop up a lot today, is just to remind you that the beta is a map that eats the omega and gives you the R dot. Okay, so the omega itself is just three numbers, so it's an R3, and the R dot is a tangent to, it lives in the tangent space to SO3 at R. So beta R is a map that eats R3 and gives you R dot. And this map is exactly the one that you know about. That you take the omega, you put it in skew-symmetric form, you multiply by the left by the R, and then you have the R dot. Okay, so this is the usual formula that you're familiar with. Okay, we just write it like this as a map. And then this system is a rotating rigid body, but we don't need to rethink of some sort of Lyapunov function on it, because by itself it already has an energy-like function. It's already the kinetic energy of the system. So h of x on this system is h of p. It does not depend on the r. Okay, you remember we said earlier when we have kinetic energy, and the kinetic energy does not depend on the rotation and does not depend on the configuration. It's always a constant if you write it in the body fixed frame, if you remember. Okay, so here similarly the kinetic energy of the system, which is as you know, it's actually half omega transpose j omega. But if we write it in terms of the p, where the p is j omega, you can rewrite it like that. This is very similar to 1 over 2m v transpose v in the point mass. Okay, does this make sense for everyone? Okay. And now the geometric control problem is simply a proportional term and a derivative term, such that this desired state, which consists of the desired configuration, the desired orientation, and zero angular velocity, we want it to be asymptotically stable. Equilibrium point of the closed loop system looks like that. So this is definitely nonlinear. It's no longer linear. You see, beta itself is actually a nonlinear map. Okay, so beta r is a nonlinear map of omega and r. And p dot, we have here multiplication of p and omega, so that's also nonlinear. And we have the torque. We're going to be designing it, expected, of course, to be nonlinear, and the derivative term, in that case, actually, it will be linear because it will be sufficient. But you're going to see, okay, we can actually make it nonlinear if we want. Yes, Fahd.
Explain what a nonlinear map is.
Nonlinear map is a map that's not linear. That's it. And a map that's linear, you already saw the definition of it, right? So a map that it goes from the vectors. Actually, it's a map between vector spaces, and it's a map that we can add two terms of it, and then you can split it, right? So beta r, for example, let's say, for example, I have r1 plus r2. It's immediately not defined, right? But beta r of omega 1 plus omega 2 is linear. Okay, you see, because I can have an r, and I can the omega tilde, the tilde map. You remember skew symmetric was actually linear. There was one problem that you had there, and multiplying it by the left is also linear, right? So that's metric multiplication, which is linear. So only this term is linear in omega, but we cannot even define the linearity in the r in this sense. Okay, this term is omega itself is actually J inverse P. So you see, as a function of P, it's actually quadratic, right? It has it's a P cross JP, J inverse P, this term, right? So it's nonlinear because it's quadratic in P. So this is a nonlinear term, okay, in P. Okay. The torque we're going to be designing for the proportional part will be nonlinear, okay? And thus this is actually a nonlinear map in general, okay? Make sense? The proportional term, we're going to be designing it as the gradient of some potential function psi of r that has a minimum at r equal r desired. And the tau desired, we're going to be designing it such that it injects damping so that the derivative of the Lyapunov function, so Lyapunov function candidate that we're going to have is usually h of p, which is the kinetic energy of the system that it originally had, and psi of r, which is the extra additional energy that we added. So it's like virtual energy. Okay, so there's only one physical rigid body rotating. However, you see that the torque, the torque term.
What does this extra energy express?
It's the energy that comes from the controller. You can think of it this way. The controller itself comes, you apply this controller through actuators, right? So this tau in the end this rigid body model that we're talking about is controlled by some tau. So let's say that there is an external supply of energy, right, to make this rotate in a way that you want. So usually the power that comes from here, okay, this is the one that we say that this is added energy to the system, virtually, of course. Okay. This is the yes, Ammar. Yeah.
Why in the Lyapunov function you didn't add any term for the derivative tau d, the derivative of the
Here.
Yeah.
The proportional term.
You said that h models the original dynamics of.
That's right. The original energy.
Tau. What is this?
So the psi. So
models the injected energy into the system, right?
The one that comes from the proportional term.
Where's the term for the tau d?
The tau d. The tau d usually comes from the damping term.
But where's that term in the Lyapunov function?
It doesn't appear here. It appears in the v dot. Okay. So the proportional term appears in the Lyapunov function. However, the derivative term appears in the v dot.
It is somewhat inside of the psi.
No, it's not in the psi completely. The psi only defines the tau p. And that's exactly what we're going to be doing now. If you tell me the psi, it's a function of r, I'll tell you the tau p, full stop. The tau d, you have full freedom to design it as you wish, and we design it such that the v dot is negative definite, or negative semi-definite.
Is this system controllable? Because what I see here, tau affect is that b.
Yeah.
Integrating b, not affect is r.
That's right.
So
It affects.
Where?
The p is and the omega, they are related. They are two coins. Actually, this I wrote it explicitly like this term, but you can simply write it as you see on the right hand side. It's a function of r, p, and omega, right?
R and omega, yes.
But p.
The above one.
Both.
R dot equal R omega delta, right?
Yeah, that's right. Omega. What?
R omega delta.
And here there is a p. That's right.
R dot equal R omega delta, right?
And the omega is what? Is J inverse p. So it's a function of r and p.
J inverse p. Can you write it? Okay.
Angular momentum, p. You multiply it by J inverse, you get the omega.
The angular momentum.
Angular momentum.
Okay, so yeah.
Not position. Psi is the position. There's actually no position here. Okay, so p is the angular momentum, omega is the angular velocity.
Okay.
And they're related by J. So written here like that, it's actually a function of R and P only. If you just remove the omega and write it in terms of J inverse P. However, written like that, okay, I never told you why, okay, but that's a secret, but it will make our analysis much easier. You'll see today actually, that actually it will just, things will drop out much easy. And if you just capital the J inverse written like J inverse P, okay, it will be technically correct, both are the same. However, it will make the analysis slightly uglier, okay? Okay? Clear? It's good that you asked that, because after that it will be very fast, okay? So this is the recipe to design the controller. We need an error between R and R desired, that's one thing. We need to define a positive definite function, psi of R, that actually characterizes this to be like an error and an error function. And then we compute the differential of that function. And then after that, we convert the differential to a proportional controller. And after that, we design the derivative controller. Okay? Make sense? The first two, we already finished them last time. So we said that the error between them is simply between R and R desired is R desired with, so RD is actually R of this frame with respect to S. And when we say only R, we mean R of that frame with respect to S. So the error of this one with respect to that one, or this one with respect to that one, is simply one transpose multiplied by the other. Okay? The convention we're going to be using is R desired transpose multiplied by R. You can also define it the other way around, like R transpose R desired. Okay? One will be defined from the left, one defined from the right. Okay? That doesn't matter. This way, this is when we say RE, this is the error we're talking about. The error as R goes to R desired, so if this one goes to that, but and another point, we're talking only about rotation here, so all of these frames are at the same point. We're not talking about translation, so we're not doing it SE3 control. That's next lecture, inshallah. So when we say R desired becomes R, so the frame desired becomes the frame B, which means R goes to R desired, we're actually thinking about the error going to the identity. Okay? And then we said this is the function that we're going to be choosing to be designing the controller. So it's half trace I minus R desired transpose multiplied by R. If we plug in here R equal R desired, you get this is 0. And we've shown before that it's equivalent to 1 minus cosine theta for some theta. Okay, and the theta goes from minus pi to pi. The theta is actually equal to 0 when R equal R desired. Okay, and it's equal to 2. That's the maximum value of it. In some cases, and we're going to be looking at that cases precisely today, inshallah.
Just a quick question.
Yes.
Between the two frames, there are 3 angles.
No angles. No angles.
Which theta here?
That's a good point. We're not talking about one, like roll, pitch, and yaw angles between. No, there is actually rotation about some axis. You remember we had the exponential coordinates earlier. Similar to the screw, exactly. So this theta had another. We said that there's something called exponential coordinates of SO3. If you give me a rotation matrix, I can. We actually did it the other way around. If you give me the theta and the n hat, right, which is the unit vector, I could transform it into the R using the Rodriguez formula. And there is an inverse formula to that because we said the exponential actually is not invertible in all spaces, but in some region you can define it to be invertible, and you can define something called the log map. Give me the R and I can tell you immediately the theta and the corresponding n hat. Okay? And then you see here actually the function does not depend on the n hat. If you remember when in the analysis that we did earlier, we had there something like the n hat, I think it was the trace of n hat and the trace of the trace of n tilde and the trace of n tilde squared. And we shown earlier that actually the trace of n tilde is 0 and the trace of the n tilde squared was something like -2 or something. Okay, you can go back to a previous lecture on that. So we've shown this earlier, which means that for all values of R, the psi lives from 0 to 2, maximum of 2. Okay, which means that it's positive definite. Okay, locally at least. Now for the control. Now let's continue. Okay, so the first step, that's also a little bit of a recap, but just this is our starting point for today. We said that the differential of the function, psi, is a covector, and it's defined as the unique covector that satisfies this equation here. So how do you read this equation? The green term is the covector, the differential, and the red term is the Delta R is what?
It's a vector.
Is any vector.
Okay.
You see, whenever you see something like this, what does this mean? For all vectors, delta R is called delta R. The vector itself is called delta R. We could have called it anything else, H, Y, it doesn't matter. We just call it delta R like that. So give me any vector and let this covector eat it. Remember, whenever a covector eats a vector, what does it give you? A scalar number. So this whole term is just a scalar number. Okay? It's equivalent to evaluating psi at some curve, we call it R epsilon down. Okay? And we differentiate that curve, and then we substitute epsilon equal to 0. Last time, this was a generalization of the definition of the differential from a vector space to a manifold. Do you remember? Last time we did the vector space version of it, and inside of this term we had x plus epsilon delta x, right? So this plus is only valid in a vector space. Here we don't have this plus, so this is the manifold version of it. And the manifold we're talking about here is SO3, so this is just written in terms of SO3, not in general on a general manifold. The R epsilon down, so R sub epsilon is a curve on SO3 that satisfies that at epsilon equal to 0, the curve starts from R, the point you actually want to evaluate here. And when you differentiate, when you look at the tangent vector to that curve at epsilon equal to 0, at the first point, so here, for example, you get that's equal to delta R, the one that you started with. Okay. So in order to find actually the co-differential, we need to, the recipe is always the same. First, evaluate the left-hand side, okay, and then evaluate the right-hand side, and just compare both, okay, by eliminating the arbitrary delta R. And whatever is left there is simply the green term. Okay. Last time we did it for the vector space. We got, you remember, it was kx transpose, something like that. And this was actually the answer to how do you differentiate, how do you find the gradient of any function in general, or the differential of any function on a vector space, instead of just memorizing and doing, all of the differentiation rules that you know. Okay. Yes, Ammar.
So I'm thinking about the manifold. There might be some points where any tangent vector to it is not 0. Yeah, all the tangents, if the manifold is curved somehow,
Okay.
all the tangent vectors shouldn't be 0, right?
Vanish at that point, you mean?
Yeah.
Okay.
They have a value.
Okay, they're not 0, yeah, okay. So? Here,
Or the other way around, sorry.
here we're differentiating with respect to epsilon.
Okay. If it's all 0, what will happen?
What is 0?
If it's if the point if the static point R is 0, it's a local minimum.
R is a point on the manifold.
Yeah.
And delta R is the vector, tangent vector, to some curve
Yes.
at that point.
I'm saying if d over d tilde, d over d psi.
This term here.
Yes. If at R it is 0 for all tangent vectors, for all tangent space. For
That's not likely. Equal to 0. It has nothing to do with that. No. This is a function of R. Okay. If it's equal to 0, then you okay. I don't know how you think about it. It's very hard actually. That the gradient of the function at R is equal to 0 for all R.
No, not for all R, for just this point.
But that's the thing. This is for all R. This is a function of R, which means that the gradient is defined for all R, for R on the whole manifold. That's the thing. So the R here is general, and the delta R here is also general. It's arbitrary. Okay. So in the end, you get a function. Okay. Imagine that you have a function of x, okay, and you differentiate and you get 0. This means actually the function is constant.
Yeah.
That's not the case here. So that's a very special case where your function is constant. That's the only thing I think about. It's not a function of R. I think that's what you're saying.
Again, what is epsilon here?
Epsilon here is an arbitrary, just a dummy variable. It's an arbitrary variable you just add, and then we differentiate with respect to it and plug.
So it is like
variation.
or okay.
This is usually related to something called variational calculus. Big topic on its own. Okay, you've seen it probably when you're talking about Euler-Lagrange at some point, but this is related to that. Okay.
So there is, for example, here R optimal curve that we wanted to reach, and there is some variation.
We never talked about the curve itself. We don't care
So
about.
the epsilon here, it is the variation from the graph, the optimal graph to the another.
No, you're thinking about now the variation calculus version when doing the action in principle. No, we're not there. No,
Okay.
this is only that. So you see, we have information about R and delta R. We're saying that vary a little bit
On the same curve.
from the same point. The whole curve, it doesn't matter, you see. We don't care about the curve. We only care about it at epsilon equal to 0. About the point and the vector of it. We do a little variation and see how the gradient changes.
But there is no vector here for R.
What do you mean? Delta R is a vector.
Delta R,
Is a vector.
delta R here, what is...
Any vector.
There's no R minus R. So what is the delta R here?
It's the tangent vector, this blue curve.
Okay, the tangent vector, okay.
Okay? It's a vector in a vector space.
So the tangent vector and the epsilon, again,
Epsilon is simply just a scalar.
okay.
It's just a number. It's actually a variable, and you differentiate with respect to it.
From this R,
Yes?
move it a little. in
Exactly.
this tangent.
Exactly.
This epsilon,
I move in this direction,
this epsilon.
and I see how the function changes.
Okay.
That's exactly the first time you might have heard it sometime along your career. You've heard something called the directional derivative,
Yes.
right? Actually, the gradient is the directional derivative. It tells you how the function changes a little bit if I move in that direction. That's exactly how it's portrayed here. Now, technically, what is you remember the first thing is that last time we give it a general definition on a manifold, and this did not make any sense. Now we have a manifold in particular that we were talking about, which is SO3. And if I give me a vector and a covector, how can I define this pairing between them? First of all, how do vectors on SO3 look like? Think of R dot. How does R dot look like? 3 by 3 matrix. A covector on the same manifold will be 3 by 3 matrix. Okay? So this is a 3 by 3 matrix, this is a 3 by 3 matrix. How can I take these two 3 by 3 matrices and convert them into one number? The trace. So you see here the general definition of the pairing between a covector gamma, and any delta R, okay, any covector and a vector on this tangent space, TRSO3, is simply given by, mathematically, the trace of the two matrices multiplied together. Okay? So this is a 3 by 3 matrix, 3 by 3 matrix, take the trace, you get one real number, full stop. So now we know the left-hand side. Now how do we do the right-hand side? Okay, we have to do it on the board because it's better to do it step by step. Okay. Yes.
Are there any limitations on sigma? The sigma there.
Which one?
Yeah, the inverted L. What is it called?
Which one? The psi?
The trace of
The trace of the gamma here?
gamma times delta. Are there any restrictions on gamma?
It has to live in the covector space.
In terms of 3 by 3 matrix.
Okay, that's a good point. We're not going to talk about it. Yes, it's not any 3 by 3 matrix.
Let's, for example, make every other element other than the trace.
Yeah, I see your point. We're not talking about it here. Yeah, in some cases, yes, you do have some restrictions. Yes, the easiest one, for example, if you have a symmetric matrix, if this was vector space of symmetric matrices, then the covector will be also symmetric matrices. This is one of the restrictions that you have. Okay, but here we're not going to go into details of it. Okay. Whiteboard. Okay. So we have psi. So first part. So first thing we're going to be doing today is compute d psi of r. Okay. So psi of r is simply half trace I minus r desired r. And the right-hand side, it was not a function of r, it was a function of r epsilon. Okay. So how is that defined? Simply half trace I minus r desired transpose r epsilon. Make sense? And then you differentiate that term d by d epsilon, and then substitute epsilon equal to 0. Okay? After the differentiation, not before the differentiation. So it's equal to the differentiation of, so first of all, this term, let me just rewrite it a little bit. Okay? The trace is a linear operator. Okay, so I have trace on general matrices. So this is a matrix minus another matrix, and taking the trace of both is simply, I can rewrite it as the trace of the identity minus half trace of R desired R epsilon. So is this a function of R?
No.
Sorry, is this a function of epsilon?
No.
Is this a function of epsilon?
Yes.
So when I differentiate this with respect to epsilon, it goes to 0. So I'm only left with that term. Okay? So I want to differentiate minus half, let's put the minus outside, and the minus half. All of it is just a constant. And then I'm left with R desired transpose R epsilon. Make sense? Okay. Sorry, trace. Yeah. The trace is a linear operator, which means that you can actually take inside the differentiation. Okay, so I can differentiate what's inside. Okay, so I'm going to have this is equal to minus half trace. Let's open a big bracket, and let's do differentiation of two matrices. You remember, if I have this matrix multiplied by that matrix, let's say, for example, just to make it reasonable, let's say that I had a function A as a function of time and B as a function of time, and then I'm telling you what's the d by dt of the product of both. What is it? A dot multiplied by B plus A B dot. Can I change the order? No, because it's not commutative in general, right? If one of them was constant, not depending on t, then that one drops. That's exactly the case that we have here. We're differentiating with respect to epsilon, which means that I have differentiation of this one with respect to that one, plus differentiation of this one, plus this one multiplied by differentiation of that one. Okay? And differentiation of this one will be 0. So I'm only left with something that looks like this. Transpose d by d epsilon, and then I substitute epsilon equals 0, r sigma. And this whole term, we already defined it before. What was it? We said this is del r. Remember, by definition. Okay. So we're left with minus half trace of R desired transpose del R. Okay. We're done. So this was the right-hand side. We've differentiated the right-hand side and we've plugged in epsilon equal to 0. Now what should we do? Compare the right-hand side with the left-hand side and just find what is the definition of this covector. And we said that this covector, the left-hand side, which is this one, so d psi of r, paired with any del r, so let me put this del r to be in yellow. So del r, and also we have, this is del r. Let me put it just in yellow. We said that this is by definition, on SO3 of course, I'm not going to write the tangent space, it's easy, it's easy to guess from the context here. This is the vector space we're talking about, TRSO3. It is simply the trace of this whole covector, d psi of r. This is a 3 by 3 matrix, and you multiply it, so this is the matrix multiplication, by del r. No, this is the definition of, give me a covector and a vector, and I multiply them together and take the trace. Now let's compare both sides. What can we conclude that this covector we're looking for is? So if you compare this one and that one, what's the conclusion? That this covector is equal to minus half RD transpose. Does that make sense? Make sense for everyone? Yes.
Before the slides, there was no trace.
Sorry?
Before the slides, there was no trace in the definition.
Which one?
The definition of the differential.
Here.
The other side.
This one.
Yes, this side that didn't have a trace.
Are you sure?
I remember.
We'll go back to it. Okay? Does that make sense for everyone?
Yeah.
Okay, clear? So we're done. Now we know what the covector is. So differentiation with respect to R, okay? Taking the gradient. Of course, the gradient now of psi with respect to R doesn't make any sense. The differential makes sense, okay? But now you remember how we defined the differential of some function with respect to something in Rn. And we said that the gradient of it is simply the transpose of that, okay? Now you might say, okay, but this is a 3 by 3 matrix. Can I say that I'm going to transpose this and then I'm going to get the gradient of it? You can. But and now you see here, both will be 3 by 3 matrices. Earlier, when we had Rn, you were able to differentiate between vectors and covectors by simply saying this is a column vector and this is a row vector, right? Here, both are 3 by 3 matrix. I transpose a 3 by 3 matrix, what do I get? Another 3 by 3 matrix. So it's impossible just to look at the matrices and say, yes, this is a vector and this is a covector. While the definition, okay, so this is just, the definition here, this is naturally a covector, and the R dot is naturally a vector. Okay, so it's impossible just by looking at how the object looks like, how it, whether it's a vector or covector. Okay? So this is the covector we were looking for. Yes, Fahd, yeah.
We multiply the covector, or we add the covector with the vector, and we should get a scalar, right?
You let the covector eat the vector.
Okay, so eating it is applying a trace or something, right?
Exactly. This is to be precise, and I don't want to go there, so ask me after the lecture, because it might confuse a little some people. Okay, if it's confusing, I have to say.
The d epsilon r is not the covector itself.
That's right. Okay. So we said earlier that a covector is a map that eats the vector and gives you a scalar number. Everything in white here is the covector as a map. Because you plug in here the vector, you get a scalar. Okay, make sense? This is exactly the same as writing the covector as a row vector, because written as a row vector, I can just let it eat a vector, and then it becomes a scalar. Okay? So the row vector form of the covector is actually also a map, similar to this one. So that's a map. Now what we did here is similar to what we did in the Rn case. When we said that, you know what? The covector written as a row vector, I can simply write it as, I can take it out, and I can write it similar to a vector. And both of them were actually column vectors, right? And you were not able to differentiate at that point. This is exactly what we did here. So it's like what we did here is that we took the map. The map is simply the trace and something, and then it eats a vector. This map is defined uniquely by this term, this 3 by 3 matrix, right? So that's exactly what we extract here. Okay? So
You're saying that the trace is part of the map?
trace is part of the covector. Absolutely, that's exactly what I'm saying. But I did not want to say it earlier.
Mathematically, the way we are going to solve it, let's say if we have some matrices,
Yeah.
is that first we let the vector delta of psi r, t psi r, eat the delta r, and then we take the trace.
No. So you say, okay, if you want, what is the covector itself? Is this one.
So we take the trace first and then let
No, it's a map, which means that it doesn't give you a number unless you give me the vector.
Okay.
For example, take f of x.
Yeah.
Is this a scalar?
No, it's a
Unless you give me the x, it becomes a scalar. That's the same. So it's written as a function of the vector. So here. So you give me that, then it becomes fixed. And then delta r can be anything, exactly the same as here. Give me r desired, I can make up this function. But it still doesn't give me a scalar unless I tell you what is r, what is delta r here. So now it becomes a function of that eats a vector and gives you a scalar number. That's exactly how it is here. Okay? So now let's go back to, so that's it for that side. Let's go back to the slides. We're going to go back and forth between the slides and the board today, okay? Because it's technically heavily today. So that's exactly what we did so far, and this is the conclusion we got. D psi of R is equal to half minus half R D transpose. Yes, Fahd.
Another question.
Yes.
What if we vectorize the matrix, for example?
No, not go there. Vectorizing the matrix is you can do it.
It's an equivalent map, right?
You can do it, but things will get very nasty. It's actually much easier to do it like this. And I can give you a reference that actually does it. And you can compare.
An equivalent physical
Yeah, of course. You'll get everything exactly the same. Yeah. Okay. Because there was something I think I mentioned last time. The trace of the multiplication of two matrices is exactly the same as the inner product, like the duality product between the vectorized versions of it. So yes, everything comes. They are isomorphic. Okay. And we said that earlier, a long time ago. I gave you an Rn by n, and I told you prove it's isomorphic with the vectorization map to Rn squared.
Yeah.
That's exactly the same.
Would it be equivalent to the trace?
It's but that's the thing. If it's isomorphic, then as a vector space, whatever I can do here, I can do there. No loss of information. Which is easier, which is nicer. I prefer this one. So that's okay. So third step done. Fourth step, so let me go back. Okay, just to remind you, our first step, compute the error. Second step, choose the psi of R, choose the potential function, and that's a choice. Okay, so this is part of your controller. You design it, you can change it. Okay, and if you have something with SO3 in your project, feel free to play around with this. Okay, you're gonna have an assignment and you can play around with this. Okay, next week inshallah. Okay, for this problem. How to compute the gradient, or the differential of that function that you chose? We just did it for that choice of function that we had. And now the question is, how do I convert a covector into the proportional torque, which is just three numbers that I can apply to my inputs, to my control inputs of the system. So this is where we're at right now. The way we're going to be doing this using something called duality of linear maps. Okay, you remember what was a linear map a long time ago? A linear map is a map between two vector spaces, this green vector space and this purple vector space, U and V. Okay, let this be a linear map between two vector spaces U and V. There is something called the dual map of A. So the dual map of A, we call it A star. A star goes between two new spaces. It goes between the dual of this one to the dual of that one. So A goes from U to V. A star goes from V star to U star. Yes.
Is it implicitly the other way around? Is it always V to U when the original A is U to V? Is it always A star is V to U?
V star to U star.
Yeah, V star to U star.
Yes.
Is it always that way?
That's the definition of it. Yeah.
And you can define it the other way around. You can define it U.
Can it be isomorphic?
So you cannot define it the other way around. I'll ask. So that's related to the same question because it's usually not invertible. Okay. I said here this is a linear map. I did not say it's a linear isomorphism. Okay, which means I can go one way, but I cannot go the other way around. Okay. It's defined between brackets implicitly. By implicitly, I mean that sometimes you cannot write it explicitly. You can just define it. This is the definition of it, and in order to find it out, you need to do exactly what we did. You need to compute the right-hand side and the left-hand side, and just compare both, and you get it out of it. Okay. So it's defined implicitly that. So this is A star, and it eats something in V star and gives you something in U star. So, alpha is any vector in V star. Okay. When A star eats it, what do you get? A U star, a covector in U. And a covector in U can eat always a vector. Sorry, a covector in a U star can always eat a vector in U. So this is this star. This is equivalent to the alpha itself, which was a covector in V star, eating or acting on the A of U, because the A of U will give me a vector in V. Okay? Take a look just to look at this expression. Make sure that you understand it. If not, I'll repeat it. Take a look to, just a moment to digest. 2 moments. Okay.
This assumes that A, both A and A star both go to the other manifolds tangent space. Right?
No manifolds. This is on vector spaces.
The other vector spaces.
That's the definition.
So we can say that A star is a new function.
It's a new function. It's a new map.
Yeah, a new function that maps V star, which is a new vector space.
It's the dual of where you went.
I know that V star is the dual of U and U star.
No, dual of V.
Dual of V. Sorry.
Yeah,
And U star is the dual of U.
that's right.
So they can be. They are a new vector spaces.
That's right.
So A star is a map that maps V star to U star.
That's right.
And they are a new vector space.
New vector space. Yeah, exactly.
Why the dual map for U equal the dual map for V?
They're not the same. So this is a real scalar number, right?
Okay.
You agree?
Yes.
And this is another scalar number.
Yes.
They are the same.
So why the equality here between them?
The scalar number that you get 5, I get from this side 5. If I get here 6, I get here 6, and so on. They are always the same number.
But why A star maps V star to U star, not U star?
The definition. That's a definition. This is a definition. It is defined by.
I mean, it's unlike A that maps U to V.
No, it's not the same. Yeah. And it's not the same as the inverse. The inverse is something else. You remember how we defined the inverse? We said that the inverse is simply the map that I go with it, and I go back, and I find for myself the same point, right? So that's not the same.
Is A star the dual of A, the A we defined earlier, or is it completely new?
What A we defined earlier?
The map A from U to V.
Yeah, A star is called the dual of A.
Yeah.
It's called the dual map of A.
Let's say, for example, the power equal F times V. So one dual the other. Okay. So the power here there is have, for example, it is A, right?
No,
Or if it is A,
no,
the force.
no. The force
The mapping here.
is the covector.
Okay, so the mapping.
The map is something that eats the function. You'll see it now. You have to wait for it.
Okay.
But we'll come to
So
it.
we can
We'll come to an
say
example.
We can have two definitions for the same thing.
What is the first definition? What's the second definition?
A and A star.
A and A star are two different maps.
And if the two maps can give us the same thing at the end.
That's exactly the definition of it. But they're not giving it directly. You see, that's the thing. So A, it eats a U. What do you get? A V.
Alpha star.
No. A eats a U, gives you a V.
Okay, V. Okay.
And the V, I can act on it with something in V star. That's alpha.
Okay.
This result, which is a scalar, is exactly the same as letting the A star eat the alpha first, give you something in U star, take the result and let it eat something in the U. That's exactly what you see here. Definition of it. And
Does it hold for all linear maps?
any linear map has something like this. By the way, you've always worked with something with the A star. You just didn't know it's called like that. I'll give you the easiest way to see it. But not the easiest. This is the truth, but maybe it will take you a lot, to digest it. I give you a map. For example, A is a 3x3 matrix, any 3x3 matrix, that eats a vector in R3 and gives you a vector in R3. You agree? Yes. The transpose of A, where does it go from? So if A is a 3x3 matrix, so A transpose, what does it act on? What does it take you from? From 3x3, from 3 to 3, from R3 to R3. Everyone agrees? If this is A, this is A transpose. Of course, you never saw it because you never knew actually there's something called a vector and a covector when you looked at it before. But from now on, you always have this case. You've already, by the way, we've worked with something like that. And you see that actually this going back and forth was done before. But this is, you need to go back and try to calculate it yourself. You remember when we said about the big adjoint matrix? How it goes from, for example, something in a twist in the B frame to something in the S frame? The add transpose went from what? First of all, the add transpose was used for vectors or covectors? For covectors. And a type of covector that we had there was wrenches and momenta. And the add transpose took you from the S frame to the B frame. So go back and watch the videos A couple of times you'll find that's true. Okay, but this is only if the map itself is something that's like Rn by Rn matrix. So it's you can think of it this way. However, in our case here, the map we're thinking about is actually the beta R. So if we want to convert, there is something that lives in here that we're interested in, okay, which is the differential of the function. We want to transform this into a covector in R, which is the torque. And of course, you're thinking of the torque as 3 numbers. However, as you know, torques, forces, and wrenches, they are all actually covectors. So if I want to relate from the differential of psi as a function of R, which lives in here, and I want to bring it back to a vector, which is a torque, I can simply compute it through the dual map that takes it from this space to that space. What is the dual to the to the torques? Dual to the torque. Angular velocity, omega. What is the dual of velocity? Linear velocity. Forces, linear forces. What is the dual of a twist, a big V, a whole wrench? What is the dual of an angular velocity alone? The torque alone. So angular velocity and torque. The angular velocity was mapped to something called R dot. And the R dot lives in here. And we know that R dot is equal to beta R multiplied by omega. Right? Sorry, beta R acting on omega. So this was a linear. Why is that a linear map? I just told you earlier, right? In the beginning of the lecture, we said that beta R, if you give me omega 1 and omega 2, I can simply just, show that actually it is a linear map. So that's actually a homework for you to show that this is a linear map. With R fixed, of course. And the dual of that is simply the beta R star. Okay? So because we know how beta R works, I can implicitly find how beta R star works. Okay? And then we're going to be able to convert the covector we just calculated into a torque. And that's exactly what we're going to be doing now on the board. So part 2, we're going to convert d psi of R to tau p. Okay. So just to remind you what we're doing, we had originally R3, and we want to go through beta R to TRSO3. And the covector we're interested in is mapped through the dual of that map to the dual space of the one with omega. Okay? So here, if there is omega, here there is the tau. They are dual to each other. And here, if there is R dot, then we have here d psi of R. Yes?
Didn't we say that the tangent space of, didn't we say omega lives in the tangent space of the identity? So why are we here?
This was the omega tilde. And then we said it's isomorphic to
R and normal?
Yeah, exactly. Okay? And that's exactly what you're saying. Actually, inside of here, actually, we said the beta R was actually so. And let me actually do it later, but let's continue with this part, okay? So if you want to know, okay, d psi of R acting on, on R dot. And by the way, it's not necessarily R dot, right? It's not necessarily R dot. Actually, to be precise, because the R dot is a specific delta R, right? We can also keep it general, okay? So actually, let's do that. But don't get confused, because it's exactly the same. So let's keep this as we did, to be an arbitrary vector, delta R. But eventually, okay, this delta R comes from some delta omega. So we know that delta R is actually defined as beta R acting on delta omega. So delta omega is one big vector that lives in R3. How does that equation look like? It is simply R multiplied by delta omega all tilde. That's simply how the equation looks like. Okay? Which is what you did several times you did it. R multiplied by omega tilde. This is simply how they are related together. Okay? Omega is only one type of vector that lives in here. I can have many versions of it. Okay? And we're going to keep it arbitrary like that. Yes?
This will be delta R, not dr, right?
Delta R, yes, sorry, absolutely, yes. Thanks, Ashad. Delta R. So that's the definition of it. And now we can plug it here. So this thing is the same as, okay, so first of all, you see this equation, okay? Yeah. Let me rewrite it as d psi of r beta r del omega. You all agree? Make sense? You see here, how does this look like? Just to remind you. So this is exactly the same as alpha A U that we had in the slide earlier. So the map we're talking about is this one. The arbitrary U is this one. And the alpha here is the one that we're interested in. Okay? And now by duality, how can we rewrite this? This is equal to, I can bring this one to the other side. So that's exactly what we're going to be doing. So I can have beta r star eating this whole covector. And then this will be paired with delta W. So this term here is simply A star acting on the alpha, and then after that paired with the U. And you see here this pairing actually is completely different. Because the pairing in the first case is a pairing on this tangent space, on this vector space, TRSO3, while the pairing here is a pairing on R3. Make sense? Okay. This whole thing, we're going to be calling it, okay, we're just going to give it a name because it's just taking a lot of space. So let's call this whole term here let's call this ER. Okay, so ER is simply defined as beta R star, and this is something in R3 star. Okay. So you see, how did we go? We said that we started by the psi, just to remind you. It was a general function of R that we chose. We computed the differential of it. We got a covector here, and we want to transform it into something that we can work with. Okay? And this transformation gave us what we call the ER. And thus, the ER here, which lives in here. Yes, Fahd.
So, we know that ER is the multiplication of R with omega, with the series vector.
Omega, exactly, yes.
So, BR star, how is it defined?
We don't know yet. That's what we want to do right now. We want actually to find it out. Okay? Make sense? Okay. So let's go to the next slide. Okay. So now we came to the conclusion that we have this scenario. So this is in R3, and this is equal to d psi of R with delta R, which is in this space. You all make sense? And we define the epsilon, the ER, the error. So this is an error function. So this is an error variable. And we defined it as beta R star of d psi of R. And it's a covector in R3. Now the question, how do we define it? If you tell me how the pairing this one looks like, we can try to guess it. So the pairing of this side is simply, so this is equivalent to ER delta omega.
Because it's R3.
This is just a 1 by 3 vector, and this is a 3 by 1 vector. And this side is equal to the trace of d psi of R. Sorry. Multiplied by this. That's exactly what we've seen before. Okay. So far, so good? But the delta R itself, so now the delta R and the delta omega, they are related together, right? So we said earlier that delta R is actually related to delta omega by this equation. So if I plug this in, so now let's take all of this information that we have and try to juggle things around. Okay, so let's take this term. So we said that, and there's another thing, another piece of information I forgot, that we already know how this guy looks like, right? What did it look like? Minus, nope, it was, yeah, exactly, minus R d transpose, minus half. So now that's all of the information that we have. Now let's see what we can do with it. Let's plug in what we know. Well, let's plug in these two into this equation and rewrite it like that. So we have that this guy is equal to the trace of, there's a minus half R d transpose multiplied by R multiplied by this guy. Make sense? Okay? Sorry, tilde. Yeah, like that. Make sense? So this is written in tilde form. And this is written in vector form. Okay? Now there is an identity, okay, that we can use here. And this identity is simply, let's see. If I take this vector, these two together, I can actually introduce two new variables. So ER tilde and delta omega tilde. Okay? And these will be on the small SO3. Remember what was del tilde, del omega, tilde form? It was a skew symmetric matrix. And this is another skew symmetric matrix. Okay? That's the skew symmetric matrix of this covector. Okay? How does this pairing look like now? So this is half trace of ER tilde delta R, delta omega tilde. Okay? There is something here that's changed, which is the half. It appeared here. We still have the trace of the two matrices. However, we have a half here. Intuitively, a skew symmetric matrix in 3 dimensions, okay, it has 9 numbers, right? But only 3 of them are independent. Remember, it has zeros, and then you're left with x1 minus x1, x2 minus x2, and so on. So actually, if you count here with the trace, you know, the x1 and minus x1, you're going to get double of that number. So this is why you have division by 2. That's intuitively how it looks like. Okay. So we have this term here. Now let's look at this expression. So if you compare these two together, what do you see?
ER delta equal RD transpose.
Minus RD transpose R. Everyone agrees? No, you cannot do that. Why?
The spaces are not same.
Is it the minus?
So what you're saying is that, so conclusion, from these two, from just comparing this term with that term, you're saying that ER tilde in tilde form is minus RD transpose R. You cannot do that. Why?
Because R is acting on delta tilde.
Because it is under the trace.
No. No. Because of the trace, no, you can do that. That's not the reason. That's actually related to, I don't know who asked the question, that actually, are there any restrictions here for this space? We said that this should be a covector, right?
Yeah.
If this is in R, so if this guy, so if ER is in R3 star, where should ER tilde live? It's a completely new space, but actually you can always guess it. What is it?
Cotangent of SO.
It's the cotangent, is the dual space of SO3 that we call SO3 star.
Yeah.
It is also the space of skew-symmetric matrices.
Yes.
So SO3 was skew-symmetric matrices. I don't know. We have a lot of spaces here. So this one is a skew-symmetric matrix, but this is also another skew-symmetric matrix, but it's of different nature. Just like this was 3 by 1, this is another 3 by 1 vector, but of a different nature. This was a 3 by 3 matrix, and this is another 3 by 3 matrix, but of a different nature. That's exactly the same here. Now this term on the right-hand side, is it a skew-symmetric matrix? In general, for any R desired and for any R. In general, you have no proof. It's not, okay? So we cannot just equate both. So we need to do a little bit of, trying to work things out. Let's see something here. So in general, this matrix, okay. So in general, this matrix, okay, is just in R3 by 3, not in the skew-symmetric matrix, the skew-symmetric sub-vector space. So there is an identity that we're going to be using. It simply says that for any A matrix in 3 by 3, and actually it's in Rn by n, by the way, you can always write it. You have that A is equal to the symmetric part of A plus the skew-symmetric part of A. You can always do that. You can decompose any 3 by 3 matrix, any n by n matrix, into a symmetric part plus a skew-symmetric part. Yes?
But this assumes that R is symmetric already.
No, we're talking about A here. Any matrix. Not talking about this one.
I'm talking any A should be symmetric in the beginning.
No.
For you to be able to take.
No, any matrix. And I'll show you how it looks like. Yes?
Could we have like multiplied the ER? The E is a skew symmetric, right?
Yes?
So what if we put in the negative sign inside and then give us the transpose?
So if you transpose this one, do you get the minus of the original one?
No, I mean we could just so we could say RD transpose R is equivalent to the E transpose.
This one. So is this skew-symmetric? That's the whole point.
But we know the other one is skew symmetric.
That's right. So you cannot equate them. That's exactly the point. You cannot say that this is equal to that one.
But this one is equal to this one transpose.
This one transpose is still skew-symmetric. If you take a skew-symmetric matrix and you transpose it, you get the minus, which is still skew-symmetric.
I want to put the negative sign, put it on the other.
Put it inside. Still, this is not skew-symmetric. I cannot equate them. Apples and oranges, two different spaces. But this will actually give us some help, okay? Because the symmetric part of any matrix A is simply given by A plus A transpose divided by 2. You can always do that. And the skew-symmetric part of any matrix A is A minus A transpose divided by 2. It's as easy as this. So plug in these two terms here for any matrix A, you'll find that this is always the case. This is actually a vector space decomposition in general, okay? So if we take that part here, so there's another actually identity. So if you take the trace, so let's say that, so let A be symmetric. So let it live in the R3 by 3, but the symmetric part. And let B be in the skew symmetric part of SO3, which is actually just an SO3 here. Oops, sorry. It's 3. Then if I take the trace of A and B, I get 0. That's something you can prove for yourself. Take any skew symmetric matrix and any symmetric matrix, take the trace of both of them, you always get 0. So let's combine these two pieces of information. Okay? This is written like that. I can rewrite this expression. I can write it as minus half trace of symmetric part of RD transpose R multiplied by delta omega tilde. Okay. And then I can do minus half again trace of the skew symmetric part of RD transpose R delta omega tilde. You all agree? Okay. So what does this, how does this ring a bell to you? This term, what do you think it will be? All of this term will actually be equal to 0, just because of this property. So going from here to here, we use this property. And going from canceling out this term, we use this property. Okay? So let me clean up this mess. So now we've shown that d psi of r with any delta omega is simply equivalent to minus half trace of the skew symmetric part of RD transpose R with that guy. Sorry. And we've shown also that this guy here, okay, on R3, so this was on TRSO3, is exactly the same as doing the tilde form of these guys, but on SO3, this is the vector space we were doing this at, and this is equivalent to half trace of this guy and that guy. And now if you compare both, now compare these two together, you get the conclusion that ER tilde is equal to, sorry, there's actually a minus sign here. There actually should have been a minus sign. Yeah. The one is correct. The one on top is correct. So actually, that this is the skew symmetric part of RD transpose R. Okay. So that's step number 4. We have one. We have. First of all, I haven't told you actually what the torque is. Okay, so actually, we derived this term, but we haven't said what the torque is. So, but you can always guess. So this is something in SO3, right? So it's a skew symmetric matrix. What can you make out of this one? If you have this term, okay, what can you make out of it? You can make out of it a vector. You can do S in, S minus, right? You know how S minus works, right? You just take, some components of the 3 by 3 matrix and you get a vector. Okay. And now I have a 3 by 1 vector. And this is a 3 by 1 vector that defines an error between the R and the R desired. So in the end, torque, the proportional term, will be simply minus Kp ER. Proportional controller on SO3. The Kp here is just a scalar number in R plus. So it's a scalar positive number. Okay. It could be a matrix, but that's I'll tell you why. So far we haven't done it for a matrix. Yes.
You want to change the
Exactly. Here we're going to be treating an error in the x, an error in the y, an error in the z in the same way, and I weight them all in the same. That's exactly what this gain is doing. If I want to have different weights, we could do it, but next time, inshallah. Any questions? So I'll stop now, okay? And if you have any questions, you can ask me.